Hi everyone, Mr. Lee here. In this video, I'm going to go over speed, velocity, average velocity, and instantaneous velocity. All right, let's begin. So to start off, let's go over speed. Now, speed, we designate it with the lowercase s as the variable, and speed is simply how much distance a object covers over a period of time. So we can say that it is distance divided by time. Now the units for speed is meters per second. The variable for speed is just s. And it is important to know that speed is a scalar. Okay, so a couple examples of a object's speed is, I don't know, let's say 25 meters per second or 17 meters per second. Notice I'm not using miles per hour because miles is not a SI unit. So that's a big X mark right there. Okay, we want meters because meters is the SI unit for distance. All right, so if we were to come up with, let's say, a practice problem, right? Let's say we have good old Mr. Lee, right? Hello, this is Mr. Lee here. Okay, so Mr. Lee needs to go to work. So he gets in his car and he drives to school. Hello, school. So this is school. All right, so he drives to school, but then there's a car accident in the middle of the highway. Oh no, this car is on fire. Okay, and so what he has to do is he has to take the long scenic route. So normally it would take Mr. Lee, let's say about, let's say it will take him 10 minutes. Okay, let's say it takes him 10 minutes to get to school. But because, and let's say the total distance, let's say it's just a straight shot. The distance is, I don't know, 3,000 meters. Okay. So if we were to figure out Mr. Lee's speed for this trip, okay, without the car crash, we would simply use the equation speed is equal to distance divided by time. All right. Now I always like to start off with the equation in its variable format first, and I do encourage you to do that as well. We know that my total distance is 3,000 meters. Okay, and my time is in 10 minutes. All right, so we have meters and minutes. Now, normally we could stop there, but I want to do this problem so that we can get a practice in with converting our units. So if we were to come up with a final answer, we would get 300 meters per minute. But I don't like that. I want meters per second. And so what I want to do here is I want to show you how I like to convert units. So if I have minutes, I have 1 minute in the denominator. So in order to get rid of the minutes in the denominator, I have to multiply minutes in the numerator, because mathematically speaking, if you have a unit in the denominator and you have a unit in the numerator, it cancels out. But canceling it out is nice and all, but we need something else to replace the canceled out unit. Let's replace that with seconds. Okay, and so right now, the number that we're going to put is the conversion factor. So we know that for every 1 minute, we have 60 seconds. So if I multiply across, now this is not the same as cross multiplication, but I'm multiplying numerator times numerator. So 300 times 1, I get 300 meters, divided by 1 times 60, 60 seconds. Okay, and if we were to simplify that, we would get 30 divided by 6, which is simply 5 meters per second. Wow, that's really slow. It's basically like I'm walking to school. All right, now let's say that we take a detour, and this is a good way of reminding ourselves the difference between distance and displacement. Okay, I take a detour and I go woo, right, and I go over this really crazy route to get to school. And for my detour route, I say that my total distance was, I don't know, 3 million. Oh my gosh, 3 million meters. It took a really long time. And the time it took, I'll just give it to you in seconds. It took me 1 million seconds. All right. 1 million seconds. So if I were to put this in equation form, I would do 3 million divided by 1 million for my speed, and my speed just simply becomes 3 meters per second. Okay, so that's just a quick little example of what speed is. It's just how fast something is moving. And the important thing here is that speed uses distance, and distance is also a scalar. Okay, all right, and therefore speed is a scalar. All right, now let's go into velocity. So velocity, I'm going to show you the equation for velocity first. Okay, velocity is the displacement divided by the change in time, okay, or the elapsed time. Now, as a quick little side note, okay, we'll do the side note over here. We know that displacement, okay, whenever we see that triangle, that means delta, which is final, so or final minus initial, so final position minus initial position. Okay, this is my displacement divided by the change in time. Now, remember, delta just means final minus initial. So if I have delta t, it's tf minus to. Okay, my starting and my stopping times. Now, I just want to do a quick little caveat here. Oftentimes, your initial position will be 0 meters. Okay, and so that just makes your displacement the final position, right? How far you traveled, oftentimes. Now, that is not always the case, so you have to read the problem carefully to really see what the starting position was. Same goes for initial time. Oftentimes, whenever we measure the time that it takes for an object to move, we start off with 0 seconds. Okay, so the change in time often becomes just the total elapsed time, which is t final. But once again, you have to really take a look at that problem to make sure that is the case. All right, so this is the equation for velocity. Okay, I'm going to put a little vector symbol above because velocity is a vector and it does require a direction. All right. Next thing I want to show you is how we can use this equation, okay, this velocity equation, to determine some graphical analysis. Okay, so I'm going to do a quick little sidebar here to show you a couple of things. First, let's sketch our graph. Okay, so along my x-axis, I'm going to make it time. Okay, ts. Now, whenever you create your graph, you always want your variable and your units side by side, and the units often are in the parentheses. Okay, and my y-axis, I'm going to make x. Now, I know this is the y-axis. Okay, I know that. This x simply means position, and we know that because we have the units after that variable. Okay, so I have a position versus time graph. We always write it in the y versus x format, so we have a position versus time graph. Now, that does look like a minus sign, but that just simply shows us that this is a y-axis versus an x-axis graph here. So this is my title. All right, so I just threw a lot of information at you. What I basically did is I created a graph, a position versus time graph. This is a graph that you will see time and time again. It is one of the most common graphs that we will use for the kinematics unit. Okay, so let's say we have a position versus time graph, and we have something like this. All right, so we have a straight line there. We have a constant position, and let's say we have a rise, constant position. I want that to be flat. Okay, and then we have a kind of little fall right there. Boom. All right, so we have this graph. You know what? I'll indicate the different points by. So this is like section 1, this is 2, and this is section 3, as indicated by those tiny little green dots. All right. Now I'll label this. This will be section 1, this will be section 2, this will be section 3, this will be section 4. Okay, so we have a graph and it looks something like this. So we know that the equation for velocity is displacement over time. So this graph can tell us the velocity for each individual section. Now, how can it do that? I'm going to show you the shortcut way first, and then we'll get a little bit more into it. So if we see a equation, okay, and within that equation we have a division, right? this division shows us the slope. And you might be asking yourself, well, Mr. Lee, how do you know that this division shows us the slope? Well, if we remind ourselves back from algebra, slope is the change in the y-axis divided by the change in the x-axis, okay? Rise over run. So our change in our y-axis is the change in position, displacement, and the change in the x-axis is delta t, which is the change in time. So if you take a look at this, delta x over delta time, that is velocity. Okay, so if we were to follow this logic train here, we can say that the slope for a position versus time graph gives us velocity. Okay, I'll say that again. The slope for a position versus time graph gives us velocity. And that is something that you need to memorize. Now, if you have a hard time memorizing, like I do, I like my method here. I take a look at the equation, and I see that it's a division. Okay, within the equation, that must mean the slope is determined by the two variables that are being divided. Okay, so if we were to take a look at this graph here without any numbers, okay, section 1, 2, 3, and 4, if I were to ask you for whatever this object is, right? So question A can be which parts has a positive velocity? Okay, which parts has a positive velocity? So I take a look at my graph, and we know, okay, according to what we just did, for a position versus time graph, the slope is the velocity. And I see, well, section 1, nope. Section 2, positive slope, so we can say parts 2. Okay, section 3, it's flat, that's not positive, and then section 4, it's going downwards, so that's a negative slope. So section 2 has positive velocity. Okay, and we can fill this out here. So which parts has a negative velocity? All right, so if I take a look at my graph, I know that velocity for a position versus time graph is represented as the slope, and I know that the only part where it has a negative slope is part 4. All right, now if I were to ask you, which parts was the object moving still? Which parts has a velocity of 0 meters per second? Okay, and so the parts where we have no slope, which is 1 and 3, has no velocity. Okay, so this is how we can look at a position versus time graph and see how slope is represented in terms of velocity. Now, if they give you some coordinate points, okay, so for example, let's do part 2. Okay, we'll do parts 2 and part 4. So let's say this coordinate point right there, this is 2, 4. Okay, and this coordinate point right here, let's say this is 7, I don't know, let's say 7 and 7. Okay, therefore this one, because it's a long straight line, this is also 7, that's my x-axis, so it can't be 7, excuse me. Increase, so let's say this is 10, 7, because it's along the same y-axis. Okay, and we'll say that this point here is, let's say 16, 0. All right, so we have individual points, and from here we can determine the velocity based on these points. So let's try that. So if I were to ask you, determine the velocity, okay, what is the velocity for part 2? Now, in order to do that, I always like to always start off with the formula in variable form first, and I do encourage you to also follow suit. And we know that displacement is xf minus x0, and we know that this is tf minus t0. All right, so I want to start off this way because for our graph here, we're not starting at position 0, we're not starting at time 0. Okay, so let's remind ourselves, what is our final position? So position is determined by the y-axis, and the final y-axis is 7. Okay, so we get 7 minus, and how do we initially start off? And the x, or for the position, we started off at position 4. Okay, so 7 minus 4. Now, if you're wondering, Mr. Lee, how did you get that, right? So if I take a look at the coordinates, coordinates are always in the XY format, okay, XY format, and our x-axis is time, and our y-axis is position, right? So I got the number 7 here because my position, my final position is 7, and my initial position is 4. All right, let's divide that by the change in time. So my final time is on my x-axis, so my final time is 7 seconds, minus my initial time, which was 2 seconds. So my velocity for part 2, okay, remember, don't forget your arrows, because it is a vector, will be 7 minus 4, which is 3, 7 minus 2, which is 5, so 3/5, which is 0.6 meters per second. We always want our units, okay? 0.6 meters per second. All right, so we have claimed that for part 3, velocity 3, we had a claim that it was 0 meters per second. Let's see if it's true. Always start off in variable form, okay? Displacement versus time. We have final position minus initial position, final time minus initial time. Okay, so if I take a look at my graph, I know that my final position for part 3 was 7 meters, and my initial position for part 3 was also 7 meters. Huh? Okay, all right, divided by my final time for part 3 was 10 seconds, and my initial time for part 3 was 7 seconds. So for here, we get 7 minus 7, which is 0, 10 minus 7, which is 3. So 0 divided by 3 just gives us 0 meters per second. All right? Now, the direction would be positive 0, because we know that vectors also need a direction. Okay, so we said that for part 4, we had a negative velocity. So let's see if that's true. Okay, so we got displacement over time. The change in position, so xf minus x0, all divided by tf minus t0. Our final position for part 4, remember position is along the y-axis, is 0, minus your initial position for part 4 was 7, all divided by your final time, which is the x-axis, which is 16, minus the initial time, which was 10 seconds. Okay, and so we get negative 7, all divided by 6, right? And that gives us a velocity of what is that? Negative 1.16, repeating, meters per second. Okay, and that negative is the direction because velocity is a vector. All right, so that's how you can determine the velocity from a position versus time graph. Now, from here, we can also determine the average velocity between whatever point. And so, you know what I'm going to do? I'm going to create a new graph because that's getting a little bit hectic over there. All right, so I'm going to do a brief little sketch, position, time, and let's say we have boom, 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 boom. Okay, so this is our position versus time graph for whatever object. If I were to ask you, so from start to finish, what was our average velocity? In order to find the average velocity, okay, you can either find every single velocity here and average them out, or here's a cool little trick. All you got to do is, so based on the time frame, so we said we wanted to find V average from start to finish. Okay, what you can do is you can just give or find the slope. So you're going to create a line from start to finish and find the slope. So the slope of this line, because we know that for a position versus time graph, the slope is equal to the velocity. If we want to find the average velocity, we just connect the 2 points, and that gives us V average. from start to finish. And you can do this for any amount of points. So for example, I'm going to do this in blue. If we wanted to find the average velocity from whatever that time is to this time, okay, all we got to do is we got to connect the 2 points. Okay, so imagine that was a straight line. I try my best. There we go. Okay, and whatever the slope is for this line will give us V average. All right. The last thing that I want to show you is a velocity versus time graph, which is different from a position versus time. So if we have something like this, a velocity time graph where this velocity is meters per second and time is in seconds. Okay, I'm going to use green here. Boom, right? Now we have like a piecewise function, like so. Boom. All right, and let's just throw something new in the mix. So if you're given a velocity versus time graph and you wanted to find the velocity, you don't have to find slope. Okay, all you got to do is you got to see what the y coordinate tells us. So this y point, whatever this is, will tell you your velocity for this portion. Okay, this y coordinate right there, whatever that is, will tell you the y velocity or the velocity here, and you get the drift. Right, so here this velocity will tell you the velocity for this portion of the motion, and here this is unique. Okay, this tells us that the velocity is changing. Okay, and that's something that we'll get into a little bit later. Alrighty, so this was Mr. Lee. We went over average velocity and speed. Let's do a quick little wrap up. Speed cares about the total distance, and velocity cares about displacement. Speed does not care about direction. Velocity does care about direction. And we also went into how we can look at a position versus time graph and find your average velocity from the coordinates. Okay, taught you a quick little way of finding a shortcut. Okay, so if you have a division within the equation and your x and your y axis are the two numbers being divided, that is your slope. And we also learned how to find the average velocity by creating a line between the 2 points. And the slope is that. And lastly, if you're given a velocity time graph, the individual y coordinate points will tell you the velocity. I'll see you next time. Bye-bye.